Bonjour, this is Jim Seitz from Colorado State University, and it's a real pleasure today to join you in the celebration of the life of Edmund Becquerel. What I'd like to focus on is the rise and now the fairly major impact of thin-film photovoltaics on electrical generation throughout the world, but primarily in the United States. I would like to first take a minute, though, to comment on the William Cherry Award itself, which is awarded each year at the Photovoltaics Specialist Conference and is very analogous to the Edmund Becquerel Award in Europe. So here is a list of the previous Cherry Award recipients, starting in 1980 with Paul Rappaport, who was the first director of the U.S. Solar Energy Research Institute, which later on became our National Renewable Energy Laboratory. I think you will recognize many of the awardees, all of whom have made important contributions to photovoltaics. Most are from the US, but some are also from Europe, from Japan, and from Australia. It is indeed humbling for me to be now included in this very illustrious group. So I will now turn to the thin-film photovoltaics, and I will note that thin films were part of a photovoltaic structure from the very beginning in 1839. So there are four things I would like to focus on. One is the impact that the photovoltaics are having at the thin film level. The second is to talk a little bit about what a thin film solar cell actually looks like, and kind of in parallel with that, or in addition to that, what thin film materials are being used. At the end, I'd like to wrap up by talking something about the strengths and the challenges with thin film photovoltaics going forward. So thin film photovoltaics have had both a commercial success and also at the cell level have been achieving pretty high efficiencies. So in terms of a commercial world, we're talking about large area panels, very much like the silicon ones, ranging from about a square meter up to over 2 square meters in area. And they're all, in this case, made by depositing thin film layers over the entire area of the panel. This allows fairly high-speed fabrication, and it reduces the capital expense involved. The power consumption during this fabrication is relatively low. The energy payback time is roughly half a year. And at the same time, the materials usage, as you might imagine for thin films, is pretty low. At the cell level, we're talking about pretty high efficiencies. Over 22% has been achieved by cadmium telluride, by what we call CIGS, and by the class of perovskite materials. At the same time in the field, we're talking about approaching 19% at the full-size panel level. The key materials being used for the thin film photovoltaics are often polycrystalline in nature, and the success of using these has meant overcoming various issues with defects, and particularly at the grain boundaries within a polycrystalline solar cell. The research challenges going forward, as you might imagine also, involve the quality of the material, interfacial defects, internal fields, and also the offsets of energy bands when we put two materials together. Here are a couple of pictures which I find pretty impressive. One is on the left there in a factory, and those are actual panels which are something over 2 square meters in area. And the more impressive thing is that starting with the glass at one end, the final full solar cell comes out the other end in something between 2 and 3 hours. The result of these panels, when installed in the field, shown on the right there, and this is a pretty large one, about half a gigawatt in the western United States. Cadmium telluride is the material, and First Solar is the manufacturer. Notice the scale there. These are pretty big fields. Fortunately, in the western United States, we have both large areas to use for the photovoltaics, and we also have a fair amount of sunlight. So I'd say now a little bit about the comparison between a silicon panel and a thin film panel. On the left there, the silicon panels consist of individual square, usually pretty square cells made out of silicon, of course, and then they're wired up, and then if you want to contact the panel itself, there are 2 wires coming out of the back, so that's fairly straightforward. And on the left there looks pretty much the same for the thin film panel. It's nice and black if it's done right. But what's really different about it is that the individual cells are not squarish like I showed on the left, but they're long and skinny. And what that allows us to do is to deposit the thin films over the entire area of the panel and then interconnect them so that we again have all the cells hooked up in series, the voltages add, and we have two wires coming out of the back. The way that works is shown at the bottom there. So starting with a piece of glass and then a metal, in this case molybdenum, and then that little cut in the green there is done by a laser scribe. And what that allows it to happen is that the left side is electrically isolated from the right side. And then we come along with CIS, in this case, for absorber material in orange, and then it's also cut, but that cut is a bit offset. And next we come to the top layer there, which is semi-transparent zinc oxide, and after it's put down, there's a third cut made. So the net result is that the bottom of one cell is electrically connected to the top of the adjacent cell. And therefore, once again, they're all in series, in this case, without having to hook them up individually, but just making these judicious laser scribes as the processing goes along. So what does this look like at the microscopic level? So this is for a cadmium telluride solar cell, and notice there's quite a few layers involved, and that's true of thin film cells in general. And if you take the schematic of the right and you translate it to an actual picture of a cross section, and notice that the scale there is pretty small, that it's about a micron and a half from top to bottom, but it reproduces all of the individual layers that you see there on the left. They're not smooth like you see in the schematic, but if you look carefully, you can see that they're all pretty conformal or continuous, which is good, so that electrically they act not that much differently from the schematic. You also notice that the individual grains there are about the same thickness as the individual layers, which is also good. But what is maybe not so good is that there are interfaces in between the grains, what we call the grain boundary issue, and that's where some of passivation research which has come into play has to be done. So what we have here are layers which are rough, but they're still conformal. Several different ways to get these layers. At the top left is physical vapor deposition, which we often call evaporation, and below that is sputter deposition, either RF or DC sputter deposition. Vapor transport deposition means using vapor carrier gas to get the materials you want to where you want them. Closed space sublimation is a form of evaporation where we get the source material and the substrate pretty close to each other, also being used extensively. Electrodeposition, that's been done in a liquid bath, of course, and works pretty well. Below that, metal organic chemical vapor deposition, and somewhat interesting over there on the bottom right, screen printing, where basically a slurry is smoothed out, no vacuum involved, into a layer, which actually can make a pretty good solar cell as well. So here's a plot of a lot of different materials which have been used for solar cells. And one of the obvious things you see is that red materials used for the crystalline materials, the crystalline solar cells are up near the top in terms of efficiency. That envelope there is kind of a practical limit to what efficiency you can expect in the ideal case at different band gaps. And you can see that the gallium arsenide is coming pretty close to that. The blue points are the thin film materials, and an obvious thing there is a whole lot of them have been tried, and a whole lot of them have not worked out so well. But I want today to mention, I guess, 5 of them. The first one, going back about 40 years or more, is copper sulfide. And there was a push to industrialize this around 1980. And you can maybe imagine why that didn't work out so well longer term, in that its position here in terms of the highest efficiency is not that great compared to some of the other ones. I'd like to also mention the opposite extreme, much more recently, are the halide perovskites and other perovskite materials, which you'll hear more about in one of other talks, but their efficiencies are quite good, and there's reason to believe that they're moving towards large-scale production as well. But in terms of what has actually happened and is happening today in terms of major impact on power production, I'd like to focus on three materials. First is amorphous silicon, which was maybe the follow-on to the copper sulfide, and also not going up real high in efficiency. And more recently, we have CIGS, copper indium gallium selenide, and the cadmium telluride, which are both being produced commercially and reasonably successfully. And those three are the ones I'd like to, the thin film solar cells, I'd like to say a little more about. First of all, I'd like to point out that there's kind of an orderly progression for many of the thin film solar cells, not including the perovskites, where we start with a diamond or a silicon structure, 4 nearest neighbors, and then half are replaced with cadmium and half with tellurium for that material, and going on from there. A quarter with copper, a quarter with indium, and half with selenium for CIS. And then a step further with 4 materials in an orderly pattern for what we call the kesterite cells. So as far as amorphous silicon is concerned, this got going in the early 70s, where the silane material, which obviously has silicon in it, was subjected to a glow discharge, and with additional dopants of both either N or P-type material, and with hydrogen to terminate the excess bonds, reasonably good material was produced. And in 1976, the first amorphous silicon cells were made at RCA in the US. At first, these were mainly used for low power and relatively inexpensive applications, but they did have an impact, and particularly visibility, because they were showing up in calculators and watches. But then the technology spread to large-scale panels, and around 2010, amorphous silicon panels were making a fairly major impact overall on photovoltaic production. They also moved towards using different layers in what we call tandem cells with amorphous germanium and with alloys. And unfortunately, the market for amorphous silicon has suffered, both because of a relatively low efficiency, which I showed a little bit earlier, and also a few other issues never were completely solved. The copper indium selenide, which initially at least was CIS, started as crystalline cells in the 1970s. And around 1980, good performance thin film CIS cells were being made at the Boeing company, which did a few things besides airplanes. In the late 80s, it was discovered that if you partially replaced the indium with gallium, you could expand the band gap, and you could also allow spatial grading of a band gap. And so that's why we usually hear about CIGS. And other variations followed with aluminum for copper, sulfur for selenium, and so on. Large-scale production has been happening in Japan, Europe, the US, and currently CIGS is second to cadmium telluride among the thin film photovoltaic materials. Here's a band diagram which kind of shows the layers for CIGS in this case, P-type, N-type cadmium sulfide, and then at the far left there, transparent contact, in this case, zinc oxide. Now turning to cadmium telluride, it also started early on with crystalline solar cells, and in 1972, the basic thin film structure, which is to say N-type cadmium sulfide, P-type cadmium telluride, was developed by Dieter Bonnet and his colleagues in Germany. In the 1980s, a fairly important thing happened. These grain boundaries, which I've mentioned, were passivated, which is to say the defects were toned way down with oxygen and even more so with chlorine. And that led in 1987 to what today is widely used as a post-deposition treatment. Most cadmium telluride cells now use the superstrate design, which I showed earlier. And in this case, the light enters through the glass. Note that you have to flip it over in order for the sun to shine in the right way. And also this layer of the alloy of cadmium selenium telluride has become quite common. So about 2000, the large-scale production by several companies of cadmium telluride got underway. And today, the first solar company has about 5% of a total photovoltaic market. But in the US, it's powering well over 30% of a total photovoltaic electricity which is being generated. To kind of wrap up, I'd like to mention, as I said, strengths and challenges. In terms of strong points, to reiterate, there's fast start-to-finish processing, which has allowed very low-cost manufacturing. Only small amounts of the key elements are needed. And the successful polycrystalline materials, after those passivation steps I mentioned in a couple places, have been amazingly forgiving, even though they look kind of messy. Cell level challenges going forward are that there's unsolved problems with grain structure, and in particular at the interfaces where the electrons and holes tend to recombine and in that case don't contribute to external current. We're looking to increase the carrier concentration in both absorbers and contacts. And probably the biggest challenge is to get everything to work right at the same time. Additional potential for thin film photovoltaics has to do with semi-transparent panels. So the thin films are fairly compatible with things going onto windows. They're also compatible with agricultural applications. They're compatible, again, in the second bullet there with flexible substrates, which means that one can imagine a roll of substrate material. And then as it unrolls, it goes through the processing step and then is collected in a second roll at the far end. Here also tandem structures, two or more cells stacked up, either as all thin films or as a thin film cell on top of a silicon cell. So with that, I'd like to finish, but I would like to thank the many wonderful students and the colleagues I've had over many years, and funding in particular from the National Renewable Energy Laboratory, U.S. National Science Foundation, and the U.S. Department of Energy. And with that, I will leave you and say au revoir.